Welcome back, everyone. Today, we're going to be talking about section 2.6, which is limits at infinity and horizontal and some vertical asymptotes. We'll deal with both of those. And what we're looking at here is a limit as x is approaching infinity of some function f that presumably has some sort of a limit itself, as well as the limit as x is approaching negative infinity. We'll call that limit m. And I want to show you a graph of kind of what I mean. Get a nice good visual going on here. And I'm going to have a horizontal asymptote here. And a horizontal asymptote down here. And this is line M. And this one is line L. And then we have some sort of a function that as we go off to positive infinity, we're approaching L. And as we go off to negative infinity, we're approaching M. So maybe we have a inverse tangent graph or something like that. So that's the idea behind what we're doing here. And what we're going to do, and I should point out that the line y equals L and y equals M are horizontal asymptotes. Of f of x. And let's take some limits. That's at our extremes here. It may be worded that way sometime, limits at the extremes. That just means off to infinity and negative infinity. Now for number one here, we'll note as x goes to negative infinity, because we're squaring that, that makes it go off to positive infinity. But the point is, the larger the denominator gets, this whole value here is going to go off to 0. So this limit in this case is just 2. Number 2 is a little bit more involved. We have a radical here, and notice that as we go to infinity, we're doing the square root of x squared. That's just x minus x. So it's kind of like they're canceling each other out in a sense, maybe. But let's find out. So I'm going to multiply this by the conjugate. That's going to be a plus there. And that's going to force a difference of squares up top. So it's going to be the radical squared. That's just going to be x squared plus 1, because the radical and the square cancel each other out, minus x squared. And you'll note down below there, you'll notice, hopefully, the x squareds are gone. So we are just left with, and again, please note that I'm writing the limit each time. You need to do that. Again, math teachers get really weird about students not doing that. And you'll notice this denominator for sure is going off to infinity, which means the entire thing goes to 0. So the limit for this one is 0. So in a sense, they do kind of cancel one another out. Let's siphon that off there. Now for number 3, what's happening is when we have a polynomial and we're doing a limit at an extreme, what's going to take over is that largest exponent. And what's happening here is because that's a positive 3, this whole thing is going off to positive infinity, which means the limit does not exist. Make sure you write the infinity down. Don't just put does not exist. Your teacher's going to want to know why that limit doesn't exist. And by you acknowledging the infinity symbol, you'll have shown the instructor that you understand why. Now, you'll note for number 4, it's the same as number 3, as far as the function goes. And what's going to happen is because it's to the 4th power, that negative infinity that we're going to, the whole thing is just going to, because it's to the 4th power, the whole thing is, again, just going to go off to positive infinity, again, because this takes over. Actually, the x to the 4th takes over. So the whole thing is going to go off to infinity there. For number 5, we're going to have the opposite effect. So as x goes to infinity, this is going to take over. So this goes to infinity times a negative value, which means the whole thing is going off to negative infinity. And ironically, x cubed is going to, again, take over. And the negative infinity means that the x cubed part is going to negative infinity times a negative 2, which means the whole thing is going off to a positive. A negative times a negative is a positive. All right, now number 7 begins sort of the classical way that we find limits. And what I'm going to do is in the top and bottom, the traditional way, so we're going to take the largest degree in the denominator, that's x squared in this case. And what I'm going to do is I'm going to multiply the top and bottom by 1 over that. The numerator and the denominator. So we end up with a limit that looks like this. 3 over x, because one of the x's cancel out, plus 2 over x squared. That becomes 1 minus 1 over x squared. Now, why did we do that? Well, now when we take the limit, you're going to notice this goes to 0, this goes to 0, and that goes to 0. So technically what we're ending up with is 0 over 1, or just 0. And by the way, that means that y equals 0 is a horizontal asymptote of this function, of this graph. Now we're going to do the same thing here. We'll do 1 over x squared. Now notice in this case, we're going up to negative infinity. Well, that's not going to change very much. Basically, the same thing is going to happen. And even off to negative infinity, each of these once again are going to go to 0. And once again, we end up with 0 over 1, which is 0. And once again, in the negative infinity and in the positive infinity, y equals 0, which is the x-axis, is a horizontal asymptote. All right, so for number 9, we're going to do the same little trick. X to the 4th is the largest exponent that I have here. We're going to end up with (40) plus 4 over x squared, or at the x to the 4th, we just with the x squared, minus 1 over x to the 4th. And down here, we just have 10 plus 8 over x squared plus 1 over x to the 4th. And each of these are going to 0 at infinity. 0, 0, 0. Which means we end up with 40 over 10, or 4. Again, that means there's a horizontal asymptote at y equals 4. All right, let's kick it up. Number 10. Now, in this case, I'm going to multiply by 1 over x. Remember, it's the largest degree in the denominator. x is going off to infinity. That's going to be 2x plus 6 minus 2 over x over 1 plus 1 over x. Now, although these are both going to 0, up top, I still end up with 2x, the limit as x approaches infinity, of 2x plus 6. And technically, I don't need that anymore. Just as long as we know that x goes to infinity, this whole thing goes to infinity. Once again, which means that the limit does not exist. All right, let's talk about e to the x and what that graph looks like. I'm not going to have enough space for both. So let me just use the back of this previous sheet. And we'll talk about e to the x and e to the negative x. The graph of e to the x looks like this. This is y equals e to the x. And e to the negative x looks like this. And here. Ooh, that's not drawn very smoothly, but we get the idea, hopefully. This is y equals e to the negative x. And we're going to keep an eye on those. And you'll notice as for this one, as x goes to infinity, y goes to infinity. And for this one, as x goes to negative infinity, y approaches 0, right? And here we have the opposite. As x approaches infinity, y is approaching 0. As x approaches negative infinity, y approaches infinity. Keeping that in mind for this next problem, next 4 problems, I guess. So for number 11, 12, and 13, so we have the limit as x goes to infinity of e to the x. We already saw that that goes to infinity. And to the negative infinity, as x goes to negative infinity, this approaches 0. Now, as x goes to infinity of e to the negative x, again, that's this one here, we are approaching 0. And as we go to negative infinity, we're approaching, once again, infinity. All right. Find the infinite limits, limits at infinity and asymptotes for the function f. All right, let's start with the vertical asymptotes. We can see that we are here, this is 0, so this is -1. And we can see that at x equals -1, we have a vertical asymptote. You'll notice as x is approaching -1 from the left side, we're going to positive infinity. And as x approaches -1 from the right side, we are also going to positive infinity. We also have one here at 2. You'll notice as we approach from the left side, we're going to negative infinity. And as we approach from the right side, we're going off to positive infinity. Let's talk about horizontal asymptotes now. And I want to draw in the horizontal asymptote as we go off to positive infinity. So we have one there. And then we also have one as we go off to negative infinity down here. And to be clear, this is y equals 2. This is y equals 4, I believe. So 0, 1, 2, 3, 4. So again, to put it in terms of a limit, we can see at the extremes, and these are horizontal asymptotes, that the limit as x approaches infinity of our function f of x is going to equal 4. And the limit as x approaches negative infinity of f of x, we are approaching 2. So these are our horizontal asymptotes. Y equals 4, y equals 2. Our horizontal asymptotes. All right, and for our last example, example 3, let's start out with the vertical asymptote, and I'm going to do this a little bit more official. So the vertical asymptote, I'm going to do the limit as x approaches. You can see x cannot equal 5/3, so that's what we're going to approach, 5/3 from the left side. And what I've done is I've loaded in my calculator that function right there. That's this one here. And I'm going to approach it something. So what is 5 divided by 3 is 1.6. So something just to the left of that is like 1.6, just 1.6. So let's try it. Let's do vars, y vars function y1, and I'm going to do 1.6. Let's get even closer. 1.666. And you can see we're going up to negative infinity from that direction. So let's go on the other side and see what it's doing. Something just slightly bigger than 1. So we'll do 1.7. Let's do vars, y vars function. 1.7. Okay, we have a positive number. Let's get even closer. Let's do 1.667. That's going to be really close. And you can see we're going up to positive infinity in this case. And that's how you know that we have a vertical asymptote at x equals 5/3. All right, let's talk horizontal asymptotes or potential horizontal asymptotes. So let's start here, limit as x approaches infinity of f of x. And it's looking like we are going to actually be approaching. Do you see that when you take it out at infinity, the +1 and -5 become very irrelevant? So do you see I kind of have a √2x? Kind of what that's going to look like when I get rid of that. That's going to be a √2 with an x. And down here I have a 3x. So what's happening at infinity, technically, we're here. Either way, when x is going off to positive infinity, this is going to be a positive √2/3 because the x is reduced. However, again, we're going back to the definition of absolute value. So in fact, let me write that out again. I put that in another video, but I'll rewrite it here. So the definition of absolute value when it's positive, it's just x when x is bigger than or equal to 0, and it's negative x when x is negative or less than 0. So when x is positive, it just becomes x over x. We get a positive √2/3. However, when we're going to negative infinity, that's negative infinity there, this becomes negative x. So we end up with a negative √2/3. So we have a horizontal asymptote at y equals √2/3 and one at y equals negative √2/3. When we're going to negative infinity, it's approaching here. We go to positive infinity, it's approaching here. I hope that was helpful.